So now we're going to talk about acceleration. And when we talk about acceleration, we do typically think of cars. You know, you hit the accelerator. So we'll see how that relates to acceleration in physics. So first, the definition of acceleration. Acceleration is the rate of change in velocity. So for acceleration to happen, there has to be a change in velocity. And notice how it says velocity and not speed. And we'll talk about why that's the case in just a second. So when we think about change from chemistry had this little delta symbol. And the delta symbol, there we go, this means change, is final minus initial. And so you might see this as well as this as an equation for acceleration. Notice on the top here, this is exactly the same equation. This one just uses delta V, so change in velocity, and this one uses little subscripts. F is for final, and I is for initial. So this is final minus initial, which is the change. Since it's a rate, it has to have a time component. So time, change in velocity over time. Change in velocity over time. Units that we might see for this, these are typically the ones that you will see most often, but we'll talk about how we can definitely recognize what a unit of acceleration is. First is meters per second per second. You might hear it said this. You can also, this exact same unit can also be written as meters per second squared. So seconds times seconds is the same as seconds squared. Now, the big thing to note is that acceleration has 2 units of time. Acceleration will always have a unit, a derived unit with 2 units of time. It does not have to be seconds and seconds. It does not have to be seconds squared. It could be kilometers per hour per second. And here we have 2 units of time. It could be meters per second per day. Again, 2 units of time. The one we're typically going to see is this meters per second squared. But note, it does not matter. It has to have 2 units of time. And this is because of this whole rate of velocity. Velocity has a unit of time, and then the rate has another unit of time, which is where the 2 units come from. So again, acceleration will be a vector quantity. Again, since velocity is a vector, then acceleration will also be a vector. What does a vector have? Magnitude and direction. And again, as a reminder, magnitude is just a number. So this is a number with unit. That's all it is. So magnitude is a number with a unit, and it has to have a direction. For acceleration, the direction is going to be expressed with a positive or negative. So positive, negative is your direction, and then your magnitude will be the number with a unit. So what can this refer to? Well, a positive acceleration means we have an increase in velocity, because that change in velocity, if it's positive, means that we're going faster, or we're increasing in our velocity. We have a decrease in velocity. That again, since it's a negative acceleration, we have a decrease in velocity. So again, that delta V is going to be decreasing. So we're going from a faster speed to a slower speed. This is still considered acceleration, even though a lot of times we give it a different name of deceleration. Deceleration is just a negative acceleration, but they are still both accelerations. Now here's where this whole vector quantity comes in. We have magnitude and direction, which means to accelerate, we can change our magnitudes. That's what these two do. increasing in velocity and decreasing in velocity are changes in magnitude, we can also change direction. So if we change direction, we're changing velocity, which means we are accelerating. Rule of thumb is there is always acceleration if you can feel it. So if you're turning a corner, or how about this? Let's go through these in order. Whenever you're in a car and you're increasing in velocity, which means you're speeding up, you can feel the car speeding up. You can feel the car slowing down when you hit the brake pedal. And what if you turn from one road to another? You can feel the change in direction. If you can feel it, there is an acceleration. This whole feeling it means that there's a force involved. We'll get more into this when we get to forces. But nonetheless, if there is a force, there is an acceleration. They go together. So to accelerate, you increase in speed, decrease in speed, or change direction. For the rest of this unit in particular, we're really going to be focusing on these two. This one is just going to be a conceptual idea, and we'll get to that more in detail later in the semester. So we're focusing here, but don't forget about this whole change in direction. So why don't we do an example? Again, like I said, we're going to focus on increasing and decreasing in speed. So we're going to use our boxes again. First thing is the givens. We are driving and increase our speed from 50 kilometers per hour to 75 kilometers per hour. So notice how we have two different speeds or two different velocities. Which one is the initial? Well, we're going from this to this. So this is where we're starting. So our VI is going to be the 50 kilometers per hour. And this is where we're ending. So that's going to be our VF. Remember, initial, final. So this is going to be 75 kilometers per hour. And then we've got 10 seconds, which is time. And we're looking for acceleration. So there's that first box. The second box is for the equation. And if we go back, look at our two equations. Since we have F and I, we're going to use this form of it. All right, so A equals VF minus VI. There's our change in time. Box 2. So now we have acceleration. VF is 75 minus our initial, which is 50. And that's all over 10 seconds. And if we do 75 minus 50, we get 25 over 10. 25 divided by 10 gives us 2.5. Now that last box says answer with units. And here's where we get a little bit of a strange unit, but we still need to make sure that final unit for acceleration has 2 units of time. It's going to be kilometers per hour, which is what this is, divided by our unit of time, seconds. So kilometers per hour per second. You can also write it kilometers per hour per second or kilometers per hour per second. So hours and seconds on the bottom. Do we care which one of these? No. All 3 of them are exactly the same unit. So example 2 says you are traveling at a constant velocity. Constant means it's not changing. So this 75 kilometers per hour is our initial and our final. So initial and final are the same number. Wants to know what is the acceleration. Since it also says constant velocity, we also know that it must have a constant direction. So we have a constant magnitude and a constant direction. Let's go ahead and do the boxes to prove the point, but anytime you see constant velocity, you will always know what the acceleration is. So initial is 75 kilometers per hour. Final is 75 kilometers per hour. This doesn't have a time, So we're just going to put t, and then we're looking for acceleration. And you'll see why we don't necessarily need that t. Same equation, since we have an initial and a final. A equals Vf minus Vi over t, change in velocity over time. And then we get 75 minus 75 over some amount of time. Well, what do we know 75 minus 75 is? It's 0. 0 divided by any number will give us an acceleration of 0. Goose egg. So if you see constant velocity means an automatic acceleration of 0. Based on units, you can give it a certain unit, so like kilometers per hour per second, kilometers per hour per day, whatever you want to use, because we don't know what this time component is. But nonetheless, the acceleration will always be 0 if it says constant velocity. And here is why. That change in velocity is 0. Without a change in velocity, we cannot accelerate. So kilometers per hour per second. There we go. So you're not always going to be able to have your initial velocity, your final velocity, your time, and looking for acceleration or any combination of that. You might be given distances. If, for example, you know that a car is going down a certain length track, like a 1 kilometer track, and it takes this much time to do that. You want to know how fast would they be going at the end. Well, you don't have the initial, you don't have the final, you don't have the acceleration. You're looking for something using a distance. Because of that, there are going to be some other equations that we're going to be using, and we call those the big three. Why is it the big three? Well, because acceleration is a big topic, and there's 3 equations. First thing we have to assume is acceleration is constant. Notice how this is different. This is not saying velocity is constant, it's saying acceleration is constant. So we're assuming that we're speeding up or slowing down with exactly the same amount of force. It's going to be either 0 or some non-zero. If acceleration is 0, then we know it's constant velocity. And if it's non-zero, then that means that we're changing our speed. The variables we're going to see in these big 3 equations are, of course, acceleration, which is A, the initial velocity, which is VI, the final or instantaneous velocity, which is VF. Notice that this is the main word. This is the main idea that we're using, which is velocity. That's our big letter. The subscripts tell us which specific velocity it is. This is overall velocity. It's the one at the beginning. This is an overall velocity. It's the one at the end for final. And of course we have D. D is for displacement. Notice these are all vector quantities, so this one also has to be a vector quantity. Now that doesn't mean in a practice problem on a test or something like that you might not see a distance of. It can be plugged into the equations just fine. But realize that for completion's sake, it should be displacement. And of course we have time. So T is for time. These 5 variables are the ones that you will be looking at and using in that first box in order to try to figure out which equation to use. So here are the equations. We have VF equals VI plus AT. This is just a different version of this one. We can solve this equation for VF and get this equation. So these two are exactly the same equation, just written in a different form. This one solves for A, this one solves for VF. Does it matter which one you use? No, because they're exactly the same equation. So over here, we'd multiply by T. And so that would cancel out. We have VF minus VI on this side, and then we have A times T on this side. Then to get VF by itself, since it's minus VI, we would add VI. And that's how you get VF equals VI plus AT. Identical equations. All right, so I'm going to go ahead and get rid of that though. I'm just proving to you they're the exact same equations, that's all. The next one is d equals VIT plus 1/2 AT squared. Notice this one is missing a VF. So we will not be looking for VF. We will not be given VF when we use this equation. This one is missing D. So again, we would not be given D or looking for D if we're using this equation. And then this one down here, we have VF squared equals VI squared plus 2AD. The one missing here is time. It's T. So we would use this equation if we are not given time and we are not looking for time. So then the big question is, well, how do you know which one to use then? Because there's 3 of them and this seems a little confusing. Well, the way that you're going to do that is you've got to fill in your boxes. First of all, you need to fill them in because each box counts for a certain amount of points in, say, a free response section of the test, but it also helps you go step by step to figure out what you are looking for and what equation you need to use. So the way to solve it, fill in those boxes. Now, you may not always be given every single number. There are some key phrases that can help you realize what givens might be given to you. So let's go through 3 of those. First is if you see something starting from rest. If it starts from rest, if you're resting, you're not moving. If you're not moving, then that means your velocity has to be 0. If you start not moving, your initial velocity will be 0 meters per second. If it says something about stopping or halting, so if an object stops or an object halts, those are implying you were initially moving and now you're not. In the end, you are stopped. In the end, you're not moving. Therefore, your final velocity will be 0 meters per second. So starting from rest is initial of 0. Stopping or halting both imply that you are ending at 0. And then there's that one again. If it says constant velocity, so make sure it says constant velocity, then your acceleration is going to be 0 because you are not changing your speed or your magnitude and you're not changing direction. Constant velocity, acceleration is 0. All right, let's try this out. Let's try using our big 3. So in example 1, this is how I like to do it. I like to underline all my numbers. I'll start there. And then I go back and read it. So a bus is traveling at 30 meters per second and accelerates at a constant 3.5 meters per second squared. All right, so if we visualize what's going on right now, we have a bus that's going a certain speed and then it accelerates. So it's starting at this speed and getting faster by 3.5. That means this must be our VI. So in that first box, we have an initial velocity of 30 meters per second. It accelerates at a constant 3.5 meters per second squared. Notice this unit has 2 units of time, second squared. That must be our acceleration. So A is 3.5 meters per second squared. And this all happens in 6.8 seconds. Seconds is time. And it says, what is its final velocity? So final velocity, VF. That is what we're looking for. So there's our box 1. For box 2, we got to figure out what equation has these 4. This is why it's important to also put that unknown in that first box, because this is the full list of variables. This is where we go back and we look at that list of 3 equations. We have VI, A, T, and VF. So let's go back. So VI, VF, A, and t. These are our four variables. The one that's missing, we don't care about, we're not given, is d. So it's going to be this one. We have VF, VI, A, and T. So this is our equation. VF equals VI plus AT. There's box 2. Box 3 is plugging everything in that we know. We don't know VF. The VI is 30. And then we're adding on extra speed. So 3.5 times 6.8. There we go. So this is where we started, and we are adding on this much speed to get to a final velocity. All right, so let's see, we got 30 here. And then we got 3.5 times 6.8. Put that in calculator, we get 23.8. And so then 30 plus 23.8 gives us 53.8. The next question is what unit do we put here? Well, we have this one in meters per second, and then this one is meters per second squared, and then this one's in seconds. Do you have to do this every time? No. I'm just showing you how you get to the final answer here with the unit. Second squared and the seconds here cancel, and so you're left with meters per second plus meters per second, which gives you meters per second. Velocity is also always going to be in a distance divided by time. So meters divided by seconds. 53.8. All right, now example 2 uses an equation that we haven't done in a couple years. And so I apologize. You do not need to worry about doing example 2. But if you want to, in terms of doing all the boxes and everything, this is going to be a 2-step problem. So using the big 3 that we're given, you have to use one equation to find A, and then once you have A, then you can find your time. If you'd like to do this one and figure out what the final answer is and see if you're doing it right, your time is going to be 6.25 seconds. That's the final answer. All right, example 3. We have a pilot stops a plane, so let's go ahead and underline our numbers here. There we go. And 484 meters, and using a constant acceleration of -8 meters per second squared. How fast was the plane moving before braking began? All right, so our first number here is in meters. Meters implies distance, or displacement, if you're being more specific. So 484 meters. This one is an acceleration, a constant acceleration. Don't let that word throw you off. It's just meaning that it's staying at this exact same acceleration. Acceleration is negative. What did that negative acceleration imply? It means it's slowing down. So negative A means this is implying that the plane is slowing down. Well, we've only got 2 givens. There's got to be something missing. Let's see, let's go back. A pilot, there it is, stops. So it stops a plane. If you stop a plane, that means initially it's going a certain speed and then it ends at a stop. So that word is one of those key phrases. VF is going to be 0. So VF is 0 meters per second. And let's see, what are we looking for? How fast was the plane moving before braking began? So we want to know how fast was it going in the beginning. That's going to be VI. That's our unknown. So notice how, yes, there's only 2 numbers, but there is that key word or key phrase that gives us our next given that we need. So we have D, we have A, and we have our 2 V's. Let's go back and look. Let's see. We have our 2 V's and D and A. Oh, there it is. It's going to be this square one. Don't get scared with the squares. All you have to do is just hit those magic little buttons on your calculator, right? Square and square root potential. All right, so we got VF squared equals VI squared plus 2AD. So there's box 2. Box 3 is plugging in. Let's see, we've got VF. That's going to be 0, and that's squared. Let's see, we don't have VI, so that's going to be our unknown. So VI squared plus 2 times the A is negative 8.0, and then D is 484. There we go. All right, so 0 squared is still 0, 0 times 0. And then we've got VI squared. So then we got to do this part, right? So 2 times negative 8.0 times 484. 2 times negative 8 is negative 16, and that times 484 is going to give us a negative 7744 in the calculator. Now another way you can write this is instead of plus a negative, is we can always change that to just a minus, right? Plus a negative number makes it to where you just subtract it, right? All right, so we have 0 equals VI squared minus 7744. Since it's minus here, in order to move it over here, we're trying to get VI by itself. We have to add 7744 to both sides. And so then we get 7744 equals VI squared. Well, we're not done yet. We got to get VI by itself. If we have a square, VI squared, how do we get rid of a square? Which color here? To get rid of a square, you have to do the opposite. Square root. There we go. And so if we take the square root of 7,744, we get an answer of 88. So now the question is what is the unit? So we're looking for VI. Velocity is measured in meters per second. The other way, you can always do it. If you're one of those you like to see where this unit comes from, this 8 is meters per second squared, right? Because that's acceleration. This is distance, which is meters. And so that's equal to meters squared over second squared. And in the very end, what do we do to that number? We square root it. And so those squares cancel and we're left with meters per second. Do you need to know this step? No. I just know that there's some people, they like to see that completion step. Why is it meters per second? All right, last example, example 4. We're starting from rest. A race car is moving 100 meters in the first 5 seconds of uniform acceleration. Again, don't let this word freak you out. It's just saying that the acceleration is going to be constant, which is one of our assumptions. We want to know what is the acceleration. So let's see, let's underline our numbers. So we're going 100 meters. Meters is D. And we have 5.0 seconds. That's our T. And we're missing a number again. Well, there's got to be a phrase in here. Let's see, let's look. Ah, there it is. Starting from rest. We start resting, which means we're not moving. Starting means initial, so that means VI is going to be 0. So over here in our givens, we also have that VI. 0 meters per second. And we're looking for acceleration. All right, so this time we have a different set of letters, don't we? We got D, we have T, we have VI, and we have A. So D, T, VI, A. Let's go look at our list. All right, let's see. We've got D, T, VI, and A. Let's see, that one doesn't have T. Ooh, here it is. D, T, VI, and A. All right, so there's our equation. The second one in the list. All right, so we got D equals VIT plus 1/2 AT squared. Notice we got to plug in T twice, right? So let's see, we got D, which is 100, VI, which is 0, times T, 5.0, plus 1/2 times, all right, that's our unknown. So let's put an A. And then T is going to be 5.0 squared. There we go. So this is our plug-in. Let's see, we got 100 equals 0 times 5.0. 0 times anything is 0. Plus. All right, now here's a very important point. That square is only for time. It is not for the entire expression. If it was, there'd be parentheses around this whole thing. So only the 5 is squared. 5 squared is 25, and half of 25, stray mark, let's get rid of that. So half of 25 is 12.5. So half, 25, 12.5, we got to make sure we bring down that A. All right, since we have a 0 here, the 0 goes away. So we have 100 equals 12.5 times A. And then how do we get A? Well, since it's multiplying, we have to do the opposite. We're going to divide on both sides. Cancels out. And we're left with A. So 100 divided by 12.5 gives us an answer of 8. Now, since we have acceleration, we know that our final unit has to have 2 units of time. This is meters. And then time was measured in seconds, and it was seconds squared. And there we go, 8 meters per second squared.